Hello everyone, and welcome back to my online course on this discrete mathematics. And here in discrete mathematics we are dealing with the number theory and methods of proof. In the previous lecture we talked about the number theory, basic thoughts on some number theory, some concepts. And here today we are going to deal with the methods of proofs. So there are a lot of different types of proofs that are available, and basically we will deal more on the first 6 parts like direct proof, indirect proof, Vacuous proof, trivial proof, proof by contradiction, proof by case. And there are few more proofs like proofs by or proofs of equivalence, existence proof, uniqueness proof, counterexample. So mostly we will go down deep and deal with some of the basic proofs, but other proofs are very useful as well. So let's directly go on and see what are these different types of proofs, what does it mean, how do we define these proofs, and let's see some examples for all these different proofs. Let's begin with the direct proof. What is the direct proof? Let's consider an implication. P implies Q. If P is false, then the implication is always true. Thus, show that if P is true, then Q is true. So basically the implication operator, we know the actual phenomena behind this whole structure. We know the truth table in fact, and to perform a direct proof, assume that P is true and show that Q must also be true. That's the basic thought. So let's see some examples. So basically this is the idea. To perform a direct proof, what we are supposed to do is that assume that P is true and show that Q must therefore be true. Let's see this example of a direct proof. Show that an even number, show that the square of an even number is an even number. That's interesting question. Let's use the direct proof to prove this statement. Let's simply rephrase this statement as if n is even, then n square is even. Well, we agree? Yes. There is no change of the original statement. It reflects the same idea. If n is even, then n square is even. Well, let's go ahead. Assume n is even. As we have seen earlier, if P is true, then we have to prove that Q is also true, for P implies Q, right? So let's assume n is even. Now we have to prove n square is even. We are assuming that n is even, thus n equals 2 times k for some value k. We know that 2 times anything implies, or it means it is an even number. Okay. N square equals 2 k the whole square, that equals 4 k square, and that again equals 2 times 2 k square. Well, when you say 2 times something, that means it is an even number. So which proves that n square is 2 times an integer, that is n square is thus an even. Yeah, that's direct proof. You are directly proving that if n is an even number, then n square is even. This example is quite straightforward. Let's talk about what is an indirect proof. Well, the word suggests indirect. We have to prove something by means of indirect way. Let's see the definition first, then the example. The implication P implies Q its contradiction is negation of Q implies negation of P. We have already seen that in one of our previous lecture, how to show they are equal. In fact, the implication and the contrapositive both are equal. So it's logically equivalent to the original implication. P implies Q is logically equal to its contrapositive, that is negation of Q implies negation of P. If the antecedent or the hypothesis, the negation of Q is false, then the contrapositive is always true. Let's see. Thus, show that if negation of Q is true, the negation of P is true. So in order to perform this indirect proof, do a direct proof on contrapositive. So we'll check this out. Let's see how this is done with an example. If n square is an odd integer, then n is an odd integer. Let's see how to show that. We have to use contrapositive. If n is an even integer, then n square is an even integer. We are going to use this function, this statement here. So if n equals 2k for some value of k, then we are saying that n square is 2k the whole square, which is 4k square. That again equals 2 times 2k square. That is even, we know that. We just seen that in fact. Since n square is 2 times an integer, it is even. So here is your direct proof. So we have seen exactly earlier, to perform the indirect proof, do a direct proof of the contrapositive. So we have seen the contrapositive is n. If n is an even integer, then n square is an even integer. So we have done that. So now the question is, when do you use direct versus indirect proof? So it's always better for us to try the direct first. Try to prove a statement using the direct proof method. If it's not clear, we always go for this direct method, and then you can go for the indirect method. If again indirect method fails, then we can go for other methods. There are a lot of other proofs that are available. So coming back to this problem here. So here the question given to us is n square. If n square is odd integer, then n is an odd integer. So we are using the contrapositive idea, which is, what is our contrapositive? Here it's something like P and Q. We talked about P implies Q, right? So we are talking about contrapositive. Contrapositive is supposed to be negation of Q implies negation of P. So the negation of Q is, if Q is n is odd number, the negation of that would be n is even number. So that's why if n is an even integer, then n square should be, so this again P is, n square is odd integer, so n square is an even integer for negation of P. That's why we have come up with this whole idea of indirect proof, and we have proved it. Okay, let's see this example. Examples of which to use. Prove that if n is an even integer and n cube plus 5 is odd, then n is even. Well, this is quite complex than the first one that we have seen. Let's see, it's not that much hard either. Let's try via direct proof. So our direct proof is that n cube plus 5 equals 2k plus 1 for some integer k. We know this is anything 2k is just even number. When you add 1 to the even number, it becomes odd. So by definition 2k plus 1 is odd. So we have to prove if n is an integer and n cube plus 5 is odd, then n is even. So n cube equals 2k minus 4, just taking 5 onto the other side. So now again n equals cube root of 2k minus 4. Well, now it's not that easy for you to say whether n is even, because definitely cube root of 2k minus 4 doesn't yield us the needed value. Since direct proof is not working in this instance, next we can go for an indirect proof. Let's go for the indirect proof. Prove that if n is an integer and n cube plus 5 is odd, then n is even. Indirect proof. So for indirect we are using contrapositive, the idea of contrapositive. So idea of contrapositive, if n is odd, then n cube plus 5 is even. So let's assume that n is odd and show that n cube plus 5 is even. So that's our contrapositive idea. So again, to emphasize, the contrapositive is nothing but negation of q implies negation of p. So n equals 2k plus 1 for some integer k. Well, n right now the n is odd number, 2k plus 1, and n cube equals 5. N cube plus 5 equals 2k plus 1 the whole cube plus 1, because our n is 2k plus 1. So we are taking the cube of that plus 5, and you are expanding by formula, and you are coming up with this value 8k cube plus 12k square plus 6k plus 6, and that again equals, if you take 2 outside, it's 2 times 4k cube plus 6k square plus 3k plus 3. In fact, 2 times any integer is an even integer. In other words, we have thus proved it. It has been proved that by means of indirect proof we can actually prove this whole statement. Well, likewise we have to see whether we could able to prove via direct proof. If you cannot prove by means of direct proof, you can go to the indirect proof and prove it. Otherwise we have to go for other proof as well. Yeah. So proof by contradiction is another method of proof. So given a statement P, assume it is false. That is contradiction, right? If a statement P is given, you are taking the contradiction of it, that is negation of P. Prove that negation P cannot occur. A contradiction exists if it cannot occur. So given a statement of the form P implies Q, to assume it's false, you only have to consider the case where P is true and Q is false. So that's what is being given. We have to assume it's false. You only have to consider the case P is true and Q is false. So by means of this proof by contradiction example, the theorem of Euclid, there are infinitely many prime numbers. Coming back to the idea that we have discussed earlier, assume there are a finite number of prime. So here again we have, when I say finite number of prime, we have P1, P2, till Pn. So these are the finite number of primes that you have there. And with this finite number of primes that you have in hand, we are trying to prove the case that is in hand. Consider the number q again, which we have seen earlier, similar to the ones that we have earlier. Q again equals P1, P2 till Pn plus 1, the one beyond the list that has been stated. So this number is not divisible by any of the prime listed. So this number is not divisible by any of the listed prime. If we divide Pi into Q, that would result in a remainder of 1 there, which means that Q is a prime number that is not listed in the prime that we have, that is P1, P2 till Pn. This whole thing contradicts our assumption that all primes are in the list. If you recall, we have just seen this same idea earlier when we talked about the prime numbers. Yes, proof by contradiction is quite a valid way to prove by means of using contradiction principles. Let's see this example. Prove that if n is an integer and n cube plus 5 is odd, then n is even. So this is what we have to prove. Let's try to rephrase this. You are asked to rephrase the whole stuff, and you are rephrasing at n cube plus 5 is odd, then n is even. Okay, thus P is n cube plus 5, and is odd, Q is n is even. So we have both P and Q in hand. With P and Q in hand, we can find and prove by means of using contradiction principle. Assume P and negation Q. Assume that n cube plus 5 is odd and n is odd. We know that P is n cube plus 5 is odd, that is the P, right? That is your P, and Q is n is even. So negation of Q would be n is odd. Since n is odd, n equals 2k plus 1, just by the principle of definition of an odd number. So n cube plus 5, when you say n cube plus 5, we are just replacing n with 2k plus 1. So 2k plus 1 the whole cube plus 5 equals this value 8 cube plus 12, 8k cube plus 12k square plus 6k plus 6, and again when you take 2 as the outside as a common multiplier, then this whole thing becomes an even number. N is an even number here. So thus we have concluded that we got Q. So this is a contradiction. We are supposed to get negation of Q, and we got Q, which is a contradiction. It contradicts the idea behind the actual assumption, right? The actual assumption is P and negation of Q. So we assume that Q is false and show that this assumption implies that Q must be true. Q must be true. Yes, as Q cannot be both true and false, we have to reach our contradiction part. That's where we come to this contradiction. So note that on that problem that we have just considered, an indirect proof proved the contrapositive. Negation of Q implies negation of P. If n is odd, then n cube plus 5 is even. We have already shown that. The proof of contradiction assumes that the implication is false and showed that that led to the contradiction. Yeah, if we assume P and negation of Q, we show that it implies Q. So the contradiction is Q and negation of Q. That's where the contradiction came in the previous example that we have seen. Q and negation of Q. Note both used similar steps but different means of proving the implication. Can you get this point? Both the indirect proof, where we use the contrapositive idea, and again we use the similar principles there to show it. And again we have proved by means of similar ideas, same steps to prove it. But this time the previous one which we have seen, which is a proof by contradiction, where we had Q and negation of Q. How other examples or how other explain proof by contradiction? Let us see how others explain the proof by contradiction, because there are many mathematicians are still working on this basic logical proofs. Suppose Q is a contradiction which is always false. Show that negation of P implies Q is true. Since the consequences or the conclusion is false, the antecedent or the hypothesis must be false. Thus, P must be true. That is the basic thought. Find a contradiction such that OR and negation of OR to represent Q. So thus you are showing that negation of P implies OR and negation of OR, or that assuming P is false leads to a contradiction. So can you check this out again? So suppose Q is a contradiction, which means always false. So you are asked to show that negation of P implies Q, that is true. Since the consequence is false, the antecedent must be false. So thus P must be true. That is the idea. We know that antecedent is false. Antecedent is nothing but, in our case, the antecedent is negation of P, that is our antecedent. If that is false, then P must be true. That is the idea. So now it takes us to the next proof, Vacuous proof. What is this? Let us consider an implication. P implies Q. If it can be shown that P is false, then the implication is always true. Yeah, if P is false, the implication is always true. By definition of implication, yes, right. Note that you are showing that antecedent is false. So that is your proof of Vacuous proof. Let us see with examples. We will consider all criminology major in Math 220 or female. Let us rephrase it. If you are a criminology major and you are in Math 220 class, then you are a female. Well, could you also use the quantifiers? Yes, to show that we can also use that. Since there are no criminology major in this class, the antecedent is false and the implication is true. So that is a basic thought. So since we have no criminology major in this class, so we can say that the antecedent is false by means of the idea that we have in hand for the implication. So that therefore the implication is true in this case. Then comes the trivial proof. Consider the implication part P implies Q, and here again if it can be shown that Q is true, then the implication is always true. That's again by means of definition of implication. So we can note that to show the conclusion is true. In the previous case, for the Vacuous proof, we have to show the antecedent, right? In this previous case, just for your understanding, in the previous case we have to show the antecedent is false. That's why the antecedent should be false. In other words, the hypothesis should be false. So that's where here we show that there is no criminology major. So once this is false, then the implication becomes true, because we are talking about the criminology major, that is your antecedent in this example here. So trivial proof is just the other side round, where we have to show that the conclusion is true. We are asked to show the conclusion is true. In the previous one we are asked to show the antecedent is false. Here we are asked to show the conclusion is true. So let's consider the statement: if you are tall and you are in math 220, then you are a student. Since all people in math 220 are students, the implication is true regardless of the antecedent. So your antecedent is, if you are tall, this is your hypothesis or antecedent, then and if you are tall and if you are in math 220, then you are a student. So this is your conclusion, right? This part is your conclusion. So regardless of, because all in math 220 are students, we can say that regardless of the thing that they are tall or not, we can conclude that they are all students. In other words, the conclusion is true. Show a statement is true by showing all possible cases. Proof by case, as the word suggests case, which means that we have to show for each and every case. It's very interesting, right? You have come across this in one of our previous parts. As you are showing the statement of the form P1 or P2 or P3 till Pn implies Q. You are showing the whole thing is true by showing all possible cases are true. All possible cases should be true. So again, P1 or P2 till Pn implies Q, and you have this equivalence operator that's equal to P implies Q and P1 implies Q and P2 implies Q till Pn implies Q. So basically that's the proof by case. Let's see and prove that with this example here. So we are asked to prove here the A by B the whole modulus equals A modulus. In fact, we are not talking about modulus here. We are asked to prove the values, the absolute values, right? We have A by B the whole absolute value and equals the absolute value of A and by absolute value of B. And we know that in this case B cannot be equal to 0. So let's say case 1, A is greater than or equal to 0, B is greater than 0. Then we have the absolute value of A equals A comma absolute value of B equals, absolute value of A equals A, absolute value of B equals B. So we have this form A by B the whole absolute value equals A by B equals the absolute value of A by absolute value of B. So case 2, that is the case 1, and here is the case 2. Again we say that A is greater than or equal to 0, B is less than or equal to, less than 0 here. So in that case B becomes minus. So we have to take absolute value of b there. So absolute value of a equals a, absolute value of b equals minus b. So we have a b the whole absolute equals minus of a by b equals a by minus b, that equals absolute value of a, absolute value of b. Case 3, a is less than 0 and b is greater than 0. In this case, absolute value of a equals minus 1, absolute value of b equals b. Absolute value of a equals minus a, absolute value of b equals b, and a by b the whole absolute equals minus a by b equals minus a by b, that equals a absolute by b absolute. So this is case 3. So in all case 3 and now your case 4 where both a and b are less than 0, in other words both are minus. So again in that case we will see that absolute value of a equals minus 1, absolute value of b equals minus b, and the whole absolute value of a and b, a by b equals a by b equals minus a by minus b, that equals absolute value of a by b. In all cases, in the end, if you consider all the cases, in the end we can show here. So there are some few things that are involved in proof by cases. Make sure you get all the cases, but at times it is not easy. In this example we have found for all cases. In all cases we got a absolute value of a by absolute value of b in the end, but at times it is not easy. The biggest mistake is to leave out some of the cases. Yes, when there is an issue, there is a problem, there is some cases which we might ignore or which we might just leave out. There is a chance. So we could have for example there are a lot of cases we may be of not sure. We could have 9 cases in the last examples, like if you have positive numbers, if you have negative numbers, and if you have zeros, and of course those additional cases wouldn't have added anything to the proof. So in other words, there are some smart ways to eradicate some of the proofs. We should be very cautious of that as well if it doesn't add any meaning to the proof that we are dealing with. Then comes the proof by equivalence, or in other words we are going to talk about the biconditional principle here. Given a statement of the form P if and only if Q, show it is true by showing P implies Q, or in fact it is P implies Q and Q implies P is true. Both has to be true. So if we are going to show here m square equals n square if and only if m equals n or m equals minus n. So we can rephrase this as m square equals n square, the biconditional or equivalence to m equals n or m equals minus n. So we have to prove in 2 parts. One is we have to prove that equals m equals n, right. So m equals n or m equals minus n implies m square equals n square. So we will take case by case again. So in first case m equals n, yeah, that has been proved, m square equals n square. In the second case m equals minus n, again we can say that m square equals n square. Yeah, that's been quite easy to show or prove it. So we can thus show this case by case to show they are proved. And again, if you are using this form m square equals n square implies m equals n or m equals minus n, subtract n square from both sides to get m square minus n square equals 0. Factor to get m plus n times m minus n equals 0. Well, it seems they are equal. Since that equals 0, one of the factor must be 0 there. So thus either m plus 1 equals 0 or m minus 1 should be equal to 0. Yeah. So in this way is again we can show that this part m square equals n square if and only if m equals n or m equals n, minus n. So this has been proved by means of this proof of equivalence. This is quite interesting principle. Then comes the proof of existence. Given a statement for some value of x, p of x. So we only have to show that some value of x, that is p of c exists for some value of c. If we can show that, then it's proved. So there are two types. Constructive, we will see find a value of c for which p of c exists. Once you show that, then it's done. So non-constructive, show that such a c exists, but don't actually find it. Assume it doesn't exist, show a contradiction. So there is another non-constructive way to show that. Let's see the constructive existence of this proof of existence. Existential proof or existence proof. Show that a square exists that is sum of two other squares, like 3 square plus 4 square equals 5 square. Show that a cube exists that is sum of 3 other cubes, like 3 square plus 3 cube plus 4 cube plus 5 cube equals 6 cube. This is kind of direct existence proof, which is constructive. Non-constructive is like prove that either 2 times 10 power 500 plus 15 or 2 times 10 power 500 plus 16 is not a perfect square. That's not a constructive existence proof. That is a non-constructive existence proof. So a perfect square is a square of an integer. So if we rephrase this whole statement given to us, show that non-perfect square exists in set 2 times 10 power 500 plus 15 and 2 times 10 power 500 plus 16. The only two perfect squares that differ by 1 are 0 and 1. So which means that any other number that differ by 1 cannot be a perfect square, but the given problem that we have, they just differ by 1, which means that a non-perfect square must exist in any set that contains two numbers that differ by 1. Thus we didn't specify which one it was. So this is kind of a non-constructive existence proof. Then comes the uniqueness proof, a theorem that may state that only one such value exists. Very unique, it's just one that exists. To prove that, you need to show the existence that such a value does indeed exist, either via constructive or non-constructive existence proof. The uniqueness that there is only one such value. Yeah, as the word suggests, there is only one such value. So we will see an example. If a real number equation 5x plus 3 equals a has a solution as a solution that is unique. So we are talking about a unique solution in which 5x plus 3 equals a. So existence proof, let's say we can manipulate 5x plus 3 equals a to yield x equals a minus 3 by 5. So is it constructive or non-constructive? Let's talk about that. Once you consider about constructive, you have to see the existence of that proof for a unique value. If there is or there are two such numbers that they would fulfill this following condition, that is a equals 5x plus 3 equals 5y plus 3, we can manipulate this to yield that x equals y. Thus one solution is unique because x and y are equal here, and we are talking about only one solution because it's a uniqueness condition. We can also show a proof by means of a counterexample. Given a universally quantified statement, find a single example which it is not true. So it's kind of a counterexample. We just prove a single example that is not true for a universally quantified statement. You know that a universal quantifier in which all things has to be true. If you have n statement, then n statement has to be proved to be true. But a counterexample is just find one single statement that is false. That's it. Then you are showing that that is not a universal statement. Well, note that it is disproving or a universal statement by a counterexample. You can just disprove the whole universal statement just by means of one counterexample. For all values of x, negation of r, where r of x means x has red hair. It says for all values of x, negation of r of x, where r of x means x has red hair. Find one person in the domain who has a red hair. So just the idea is to find one. So every positive integer is square of another integer. The square root of 5 is 2.236, which is not an integer. So if you just prove one thing, then it's fine. You don't need to prove the whole case, all cases. We don't have to prove all cases. That's an example in which we can say how counterexample acts. A note on counterexample here, you can again disprove something by showing a single counterexample. You can find an example to show that something is not true. Once you show that, you just proved it. You cannot prove something by examples. Yeah, for instance, prove or disprove that all numbers are even. Proof by contradiction, 1 is not even. Invalid, we have the proof by example 2 is even. So this is a simple way to have this counter examples. Then finally we have some things about the mistakes that we perform, mistakes in proofs like modus borders, where fallacy of denying the hypothesis. Sometimes we have the fallacy of denying hypothesis or fallacy of affirming the conclusion. These are some of the mistakes that we might come across. Proving the universal by example, it's very hard. In fact, you can only prove an extension by example, because universal is like for everything you have to do it. That's quite hard. Disproving an extensional statement by example, again, that's not easy. You can easily disprove a universal statement by example, but not an extensional statement. This are the parts that I want to discuss with you today. So we have in fact seen a lot of things today, different types of proofs, and these are very basis for our discussion on proofs that we are going to have, and we will talk about more about the strong, weak inductions later on in one of our lectures, where all these principles that we have studied in this proof might be very useful. So just spend some time to explore more about this proof by yourself. Try to find more examples and solve these problems, whether you can able to come across the ways to prove or disprove a certain proofs that we have studied today. Okay, have a nice time, and until next time, goodbye. We are looking forward to see you in the next lecture. Until then, goodbye.